Hello everyone, and welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring the fascinating topic of inverse trigonometric functions. On this first slide, you see the title prominently displayed. We'll briefly cover what inverse trigonometric functions are, why they matter, and how they fit into the broader world of mathematics. So, let's dive in and explore this engaging subject together. Now, moving on to slide 4, which focuses on the conclusions. Here, we'll summarize the key takeaways from our discussion on inverse trigonometric functions and their derivatives. It's important to understand how these derivatives are derived and how they relate to the function's graphs, which we covered earlier. This slide helps us tie everything together by highlighting the main points we've learned. We'll also briefly touch on the significance of these concepts in broader mathematical applications. So, let's see how all these pieces fit into the bigger picture of calculus and mathematical analysis. Inverse trigonometric functions are essentially the inverse counterparts of the basic trigonometric functions. These include sine, cosine, tangent, cotangent, secant, and cosecant functions. Sometimes you'll hear them called Elcaas functions, antitrigonometric functions, or cyclometric functions. Their main purpose is to find angles when you know the ratio of sides in a triangle. This makes them incredibly useful across various fields. For example, in engineering and physics, they help solve problems involving angles and measurements. In geometry and navigation, they are essential tools for calculating directions and positions. So, understanding these inverse functions is fundamental because they bridge the gap between ratios and angles, allowing us to solve many practical problems efficiently. Inverse trigonometric functions are also known as arc functions, and there's a good reason for that. When we input a value into these functions, they tell us the length of the arc needed to produce that particular value. It's like working backwards from the sine, cosine, or tangent to find the angle itself. These inverse functions perform the opposite operation of the regular trigonometric functions, which means if sine, cosine, tangent, cosecant, secant, or cotangent give us a ratio, the inverse functions help us find the angle that corresponds to that ratio. Now, these functions are especially useful when we're working with right triangles. Remember, in a right triangle, if we know two sides, we can use these 6 key functions to find the measure of the angle. So, in essence, inverse trigonometric functions are essential tools for solving triangles and understanding the relationship between angles and side lengths. They really complete the picture of how angles and ratios connect in trigonometry. Now, let's take a closer look at the basic inverse trigonometric formulas. These formulas are fundamental because they help us understand how the inverse functions behave, especially when dealing with negative inputs. For example, notice that for the arcsine function, sin of negative equals the negative of sin of x. This shows us that arcsine is an odd function within its domain of -1, 1. Similarly, for arccosine, we see that cos of negative x equals pi minus cos of x. This reflects the symmetry of the cosine function and helps us find angles in different quadrants. When we look at arctangent, tan of negative x equals negative tan of x, which again highlights its odd function property, and this holds for all real numbers. For arcotangent, cot of negative equals pi minus cot of x, showing a similar symmetry but in a different context. Moving on to secant and cosecant, sec of negative equals pi minus sec of x, and cosec of negative equals negative cosec of x. These formulas are key because they allow us to evaluate inverse trig functions for negative inputs efficiently and accurately. They also reinforce the idea that many of these functions have specific symmetry properties, which are crucial when solving equations or analyzing functions in broader contexts. Understanding these relationships helps us connect the behavior of inverse functions to their original counterparts and is essential in mastering trigonometry as a whole. Let's take a closer look at the 6 inverse trigonometric functions listed here. We have arccosecant, arctangent, arcsecant, arccosine, arcotangent, and arcsine. These functions are essentially the inverse counterparts of the basic trigonometric ratios. They help us find the angle when we know the value of a ratio. It's important to remember that each of these inverse functions has its own specific range, which makes them useful for solving different types of problems. For example, arcsine and arccosine are often used when working with right triangles, while arctangent is very handy when dealing with slopes or angles in coordinate systems. Now, when we graph these inverse functions, you'll notice they're quite different from their original trig functions. They typically have restricted domains to ensure they are functions. That is, each input has exactly one output. Understanding these graphs is key to solving inverse trig equations and applying them to real-world scenarios. Overall, these inverse functions expand our toolkit, allowing us to work backwards from a ratio to find an angle, which is essential in many fields like engineering, physics, and mathematics. Recognizing their graphs and properties helps us connect the abstract concepts to practical applications. Let's take a closer look at the arcsine function. As you can see, it is the inverse of the sine function, which we often write as sin x. This means that if you have a sine value, the arcsine helps you find the original angle. On the graph, the arcsine function is represented visually, and it's important to understand its domain and range. The domain is from -1 to 1, which makes sense because sine values only fall within this interval. The range of the arcsine function is from -π/2 to +π/2, or π/2 to π/2, reflecting the angles for which the sine function is invertible. This relationship is key because it allows us to reverse the sine process within these specific bounds. Recognizing these limits helps us accurately interpret the inverse function and its graph. Connecting this to our overall theme, understanding inverse functions like arcsine deepens our grasp of how trigonometric functions relate to each other and their applications in solving real-world problems. So, let's talk about the domain and range of the arctangent function. Therefore, the inverse of the tangent function can be expressed as y equals tan inverse x, or arctangent x. This means that when we want to find the angle whose tangent is a given number, we're using the arctangent function. The arctangent function is essentially the inverse of the tangent function, and it's denoted by tan inverse x, or tan x. On the graph, you'll see how this function behaves, and it's important to understand its key characteristics. The domain of the arctangent function is all real numbers, which we write as infinity to infinity. This makes sense because you can plug in any real number into the arctangent function, and it will give you an output. Now the range is where things get interesting. The output values, or the range, are limited between π/2 and π/2. In other words, the function only outputs angles within this interval, which corresponds to the principal values of the inverse tangent. Understanding these domain and range restrictions is crucial because they define where the function is valid and how it behaves across different inputs. This also connects to our overall theme of understanding inverse functions and how they relate to their original functions in a more visual and conceptual way. Let's look at this example. Sin inverse of sin of π/6 equals π/6. This is using a key identity. Sin inverse of sin of x equals x. It's a straightforward case because π/6 is within the principal domain of the inverse sine function, which makes the calculation simple. Now, moving to the solution, we're asked to find the value of sin inverse of sin of π/6. Since π/6 is within the domain, the inverse sign directly gives us π/6 as the result. However, I want to highlight an important point here. There is no value of x for which sin x equals 2. That's because the sine function only outputs values between -1 and 1. So, when we see sin inverse of 2, it's actually impossible to find a real that satisfies that equation. In fact, if we try to write it out, it would be sin inverse of 2, which isn't defined within the real numbers because 2 is outside the range of the sine function. To clarify, for this kind of problem, the key is understanding the domain restrictions of the inverse sine function. When the sine of x is outside the interval -1 to 1, the inverse sign simply can't give us a real solution. So, in summary, whenever you see sin inverse of a number outside the range -1 to 1, you know that it's not possible to find a real that satisfies that equation. Let's take a moment to look at the key references that underpin the material we've discussed today. First, we have Christian Felix Klein's work from 1932, translated in 2004, which provides a foundational perspective on elementary mathematics from an advanced standpoint, covering arithmetic, algebra, and analysis. This text is instrumental in understanding the theoretical underpinnings of the concepts we've explored. Next, there's the comprehensive book by Dennis G. Zill and Patrick D. Shanahan on complex analysis with applications, published by Jones and Bartlett. This resource offers practical insights and applications that deepen our understanding of complex functions and their behaviors. Finally, we have H. Wang Qianli's 2005 paper, which presents an elementary derivation of Euler's series for the arctangent function. This work highlights elegant methods to derive important series, illustrating both simplicity and depth in mathematical reasoning. Together, these references connect our exploration of the mathematical concepts, showing how foundational theories, practical applications, and elegant derivations all come together. They remind us of the rich, interconnected nature of mathematics and its ongoing development through scholarly work.